Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems, and this module we learn about page replacement algorithms. So, the learning objectives for this module are to understand what is meant by page replacement, to understand this least recently used page replacement algorithm and different approximation algorithms to this LRU replacement, and counting based page replacement algorithms and page buffering algorithms. So, what is page replacement? In demand paging, a page is brought into memory only when it is needed. That is, when you have a process with so many number of pages, all the pages are not kept in memory at the same time. Only the currently used page or only the page that is currently needed is brought into the main memory. And when this page is brought into the main memory, if there is no free frame in the main memory, you cannot bring in this page. So, you need to choose a victim page which can be moved out so that you can bring in the required page. So, this victim page is chosen based on some algorithm. So, that is chosen based on some page replacement algorithm. So, we have a number of page replacement algorithms, and we learned in the earlier modules about how the first in first out page replacement algorithm, the optimal page replacement algorithm and the least recently used page replacement algorithms work. And now we will continue from there. We will continue to look at more different types of page replacement algorithms. So, in LRU replacement algorithm, the page which was least recently used is chosen for replacement, and there are a number of algorithms which approximate this LRU replacement algorithm. So, for this, the support is provided by using something called the reference bit. So, what is done with each page? In the page table entry, there in the page table there are a number of entries and there is an entry corresponding to each page. So, along with each page a bit is associated which is called the reference bit. Initially, the bit is set to 0. Whenever the page is referenced, the bit is set to 1. So, if 1 is existing earlier, then you need to replace the 1 which is 0. So, if you are trying to replace a page, you look for a page which has not been referred to recently. If the bit is set to 1, then it means that the page has been referred to. If the bit is set to 0, then it means that the page has not been referred to. So, when you are trying to replace a page, you replace a page for which the bit is 0. But we do not know the order in which the bits were set. Suppose if you have 4 pages for which the bit is set as 1 and say there are 2 pages for which the bit is set as 0, then you understand that 4 pages have been referred to, but we do not know which was the one that was recently used or which was the one that was least recently used. And if there are if for all the pages if the bit is set to 1, then we really do not know which was the one that was not used recently. So, we only know whether the particular page was used or not using the single bit or using the single reference bit. So, what was done? Some additional reference bits were added, that is, more history was stored, and that algorithm was called as this additional reference bit algorithm. So, in additional reference bits algorithm, already existing bits are all saved onto a 8-bit byte, and the already existing bits are shift to the right when you are trying to bring in a particular page. And then you choose the page with the lowest number as the least recently used page. And if there is a tie between two different numbers, then that is the tie is broken using first in first out. and the number of bits in the history can also be varied in the case of additional reference bit. We will see in this example how this additional reference bit algorithm works. Assume that there are 5 pages, page 0, 1, 2, 3 and 4, and in this I have shown the reference bit, and in this I have shown the additional bits. So, this reference bit is initially 0 for all the pages, initially that there is no page that has been referred to, and then this additional bits you have it is an 8-bit byte that is being used for each page. So, for each page you have a storage of 8 bits, or a history about 8 bits is stored for each page. And then in this example, you see that this page 1 and page 3 have been referred to. And what is done is that periodically you try to look at the reference bits and update in this 8 bytes that are corresponding to each of the page. So, now at this particular moment, when you are trying to update this set of bytes, you find that page 1 is referred to and page 3 is referred to. So, what is done? All these reference bits are copied on to the most significant bit here, and then see what happens next. You are copying all these onto the most significant bit here. So, page 1 was referred to, so the most MSB becomes 1 here, and for page 3 also the MSB becomes 1, and these bits are cleared now. Okay. And now at this particular time, if a page had to be chosen for replacement, you find that page 1 has some value, page 3 also has got some value, and page 2, page 0 and page 4 have got values of zeros. So, if one of these 5 have to be chosen, the one that will be chosen will be either page 0 or 2 or 4. If you are going to use first in first out to break the tie between 0, 2 and 4, 0 will be the page 0 will be the one that will be chosen for replacement. Now, say in the next instance there is a reference to page 1 and to page 2. Now, and if you are trying to copy this onto here, what you will do is whatever is there in MSB will be shifted to the right, or all bits will be shifted 1 bit to the right. Each byte will be shifted 1 bit to the right, and this will be copied on to the MSB. So, now what happens? So, there is a reference to page 2 and that is being moved on to the right, and there is also a reference to page 1 that is also copied here, and whatever was here earlier was shifted 1 to the right, and you have this value. Now, among these, now which one was the recently used, most recently used, or the best page, not the best page for replacement? There is page 1, because page 1 was referred to in the previous instance and also in this instance, and hence page 1 has got a higher value compared to the other pages. Page 2 was used recently and has this value, and page 3 was used in the earlier instant, but now it is not being used, and hence here this page 3 has got a lower value compared to page 2. But page 0 and page 4 were not used at all, and hence page 0 has got the page 0 and page 4 has got the lowest value, that is 0. So, of all these pages, when you are choosing the one that was not used recently, it will be the one which has got the lowest value. So, page 0 and page 4 are good candidates or good victim pages which can be chosen for replacement. And similarly, likewise, you can keep on adding bits here, you can keep on adding the references here, moving the references to the MSB and keep on shifting all these bits one to the right. So, at any particular time, the page that has got the lowest value will be the one that is chosen for replacement. So, this is called the additional reference bits algorithm. So, this you need this you record the reference bit at regular intervals and time, and hence it will give you an additional information about the ordering. You will not just know that whether the page was used or not, you also will know the order in which the page was used, because you have more number of bits that are maintained. And then you have another algorithm called the LRU approximation second chance algorithm. The second chance algorithm is basically a FIFO kind of algorithm, but after selecting a page for replacement, you check its reference bit, and if the reference bit is 0, then you will go to the next page. If the reference bit is 1, then it means that the page was referred to recently. So, what you do, you set that reference bit back to 0 and you leave the page in memory itself, you do not choose it for replacement, you change the arrival time to the current time. So, this page will be looked at as a page that was referred to recently, and if it is going to be a FIFO kind of, because it is going to be a FIFO kind of replacement, when you are changing the arrival time to the current time, it will be moved back in the queue. So, whichever came in first will be selected for replacement, but now we add one additional info into this. If the page was referred to recently, you add it to the end of the queue. If you are using a queue for the implementation, you add it to the end of the queue, so that it will not be considered for replacement immediately. So, look at this example of how this second chance algorithm works. So, this refers to the set of reference bits. So, for each page you have got a reference bit. So, for the first page it is 0, 0, then 1, 1, etc. and so on. And you maintain this queue of circular queue of pages. So, at some particular time, the next victim to be chosen will be pointed to by using a pointer. So, now say here the pointer is pointing onto this page, and now there is a need for page replacement, say. So, you look at the page pointed to by the pointer, and you find that the reference bit of that page is 1. Because the reference bit is 1, you try to give that page a second chance. That is, the page was used recently, so you do not immediately choose it for replacement. You change the reference bit to 0 and then move on to the next page to check. And again here the next page, you see that the next page was also referred to recently. So, what is done, the next page is also not used immediately. For the next page also the reference bit is changed to 0 and you move on to the next. Because the next has got 0 value, then it is a page that was not referred to recently, and hence you can choose this page for replacement. And suppose the worst case, what you can see here is that you can have all the reference bits set as 1 for all the pages, and then in that case you will have to traverse one round checking all the pages or the reference bit of all the pages and changing all of them to 0, and then again you find that there is no page with this value set as 0. So, you come back to this first page which you had checked and take that for replacement. So, basically you see here that it is a first in first out kind of replacement algorithm, but you just choose one after the other using first in first out. But if you find that a page was referred to recently, then you move it to the end of the queue and give that another chance before the other pages. So, this is a second chance algorithm, or it is also called a clock algorithm. And then you have another algorithm called the enhanced second chance algorithm. In enhanced second chance algorithm, we use another bit along with the reference bit. So, you have one modify bit also been added along with the reference bit. So, what is this modify bit? We have already learnt that whenever a page is modified, the modify bit will be set. So, once a page is brought into the physical memory, into the main memory, it is not necessary the contents of the page should be modified. the contents of the page may or may not be modified. It can even be a read only page which need not be modified at all. And say suppose if it is a text page or a page which has got instructions, that page will not be modified at all. So, in that case, when you are bringing in a page from the secondary storage device into the main memory, and if a copy of that page is also kept in the secondary storage device, and if you bring only a copy of that page into the main memory, and if this page in the main memory after being brought into the main memory, if it has not been modified at all, then you do not have to write this page back to the secondary storage device. So, you have this modify bit along with the reference bit to decide whether or which page is the best page to be replaced. So, if the combination goes like this, say if the reference bit and the modify bit are 0, then it means that the page was not modified as well as the page was not referred to recently. So, this is the best page which can be chosen for replacement. It was neither modified, it was not used recently. Suppose if it is 0, 1, the reference bit is 0, which means the page was not used recently, but the modify bit is 1, which means that the page has been modified after having brought into the main memory. So, this page, because it is modified, if you are choosing this page as the victim page for replacement, this page should be written to the secondary storage device before you bring in some other page into this particular place. So, this is a not recently used page, but it is a page that was modified. So, this page needs to be written before replacement. And the next page is 1, 0, the option is 1, 0, that is it was a page that was recently used, but it is clean, but probably it will be used again soon. Okay, so, it has not been modified, so this gets a lower priority. And then it is 1, 1, it is a recently used page as well as modified page, and hence you assume that it may be used again and it also has to be written to the disk. So, this is not the proper page which can be chosen for replacement. So, between all these 4 cases, the one or the page that is the best to replace or to be considered for replacement is the page which was not recently used as well as not modified. And then you have a number of algorithms called the counting algorithms. In counting algorithms, what is done? You maintain a count of the number of times references have been made to a page. Okay, so, along with a page, you maintain a counter. In the case of least recently used, we just check whether it was recently used or not. But here in counting algorithms, you need to check how many number of times it has used. So, based on the count of the times the page was used, we have 2 algorithms. One is the least frequently used algorithm and the other is the most frequently used algorithm. So, in least frequently used algorithm, you need to choose the page which has got the smallest count. So, what does this mean? This is a page which was not used many number of times, or it was not used frequently, or it was least frequently used. So, the argument for this kind of LFU algorithm is that probably this was a page which was actively used and hence has got a larger count. So, you need to look at a page which has got the least count and choose it for replacement. But because if it is a page which has got a large count, and suppose if it was a page which was used initially for a many number of time and hence the count is very high, but it may not be used at all in the future, but why do you keep that page? So, there is a negative argument that you have for LFU algorithm. The LFU algorithm, for the LFU algorithm, the positive argument is that you look at a page which has got the smallest count and replace, because you assume that it was not a page that is actively used, it is not used many number of times, and hence it may not be used in the future also many number of times. That is what you look at. In MFU algorithm, what is done is that the page which has got the most count or the highest count is chosen for replacement. So, the MFU algorithm is that the page which has got the smallest count may be a page that was only brought into the memory very recently. So, it will be used in the future more number of times. So, there is no point, or you should not remove this page and take it to the backing store, because it will be used in the near future. So, they try to look at a page which has got a higher count, assuming that that page was used many number of times, and hence in future it will not be used more, and hence you choose that page for replacement. So, this is LFU, least frequently used, and most frequently used are two count based algorithms that are used for page replacement. And then you have page buffering algorithms. And these page buffering algorithms, they are used in addition to the existing page replacement algorithms. So, you can use some kind of page replacement policy to choose the victim page. In addition to that, you can use these page buffering algorithms also. So, what is done in page buffering algorithms? The system keeps a pool of free frames. That is, you need to have a free frame in the physical memory into which you bring in your required page. And suppose if there is no free frame, you need to choose a page replacement algorithm policy. And what is done here is that the system keeps some minimum number of frames as always as free frames. And when a page fault occurs, whenever there is a page fault, a victim frame is chosen among one of the frames present in the main memory. You choose a victim frame which can be chosen for replacement, okay, which can be moved outside, so that you can bring in the desired page. And what is done after choosing this victim frame, you do not write this victim frame immediately into the secondary storage device. Rather than that, what is done? You bring in the required or the desired page into one of the free frames that you have kept in the pool of free frames, and you start working for that particular page. That particular page's work can be started. But this victim frame is later written out into the secondary storage device, so that, and because of that, what is done? The time required to move out and then move in is reduced. The time needed to write this victim frame to the disk and after that bringing in the required page is not needed. So, the time needed to write out is reduced and you can start work much quicker. And after writing this victim frame into the pool of free frames, this victim frame can be added to the pool of free frames and it can be used later. And so, here we see that it is an optimization in reducing the time to service this page fault. And then that was one way of page buffering algorithm. And the second case, what is done? You maintain a list of modified pages. So, I told you that you have a modify bit which you can keep along with the reference bit. Whenever a page is modified, the modify bit will be set for that particular page. And when the paging device is idle, that is, whenever you do not have any disk IO happening, writing to the disk or reading from the disk happening, then at that time what is done is that the pages which are modified or the pages for which the modified bit is set or chosen or looked at and they are written to the disk. So, and then the modified bit will be reset back to 0. So, because of this, what is the advantage? Whenever you look at a page for replacement, you will most probably have, or you will most probably look at a page which is not modified or which is clean, so that you do not have to write it to the disk before bringing the required page. So, this increases the probability that a page is clean when you are choosing it for replacement. And the next kind of page buffering algorithm is to keep a pool of free frames. And then you need to remember which page was present in that frame. So, where you can add a set of pages into the pool of free frames. We just now saw that we choose a victim page for replacement and then you write that to the disk later and add that victim page to the pool of free frames. And when you are adding that victim page to the pool of free frames, you also remember which content was kept in that victim frame earlier. Say if it was the contents of page 4 or page 3 and so on. So, that is remembered. So, because of this, what is the advantage? If you need the same page again. So, if the same page P4 is needed again, you can just like that take it from the pool of free frames. You do not have to read it from the disk and then continue execution, because you already have the contents, but only thing is it is being added to the pool of free frames. So, whenever there is a page fault, say for page 4 there is a page fault, first you look into this pool of free frames to find out if page 4 is present in the pool of free frames. If it is present in the pool of free frames, you can just like that take it and you can use it. If it is not present in the pool of free frames, then you need to select another free frame and then bring in your page into the physical memory. So, these are so you have three kinds of page buffering algorithms. So, now we will summarize whatever I have taught you in this class. LRU page replacement policy is the one in which you look at the page that was not used recently and choose that for page replacement. There are a number of approximation algorithms that approximate this LRU page replacement policy, and in LRU approximation you add a reference bit, a support of the reference bit is used for page replacement. So, using this reference bit you can go for the additional reference bit algorithm, or you can go for the second chance algorithm, or you can also include the modify bit along with the reference bit and use that for page replacement. And then there are a number of count based algorithms where you count the number of times the memory reference is being made, and based on the number of times you decide whether a page can be replaced or not. So, you have least frequently used and most frequently used algorithms in this count based algorithms. And then you have a number of page buffering algorithms where you can keep pages or in a pool of free frames. You can keep a pool of free frames and then you can use that, so that you can reduce this time required to service a page fault, that is writing to the secondary storage device or reading from the secondary storage device into the main memory. All these can be, at least one way can be reduced in page buffering algorithms. So, the references, acknowledgement. Thank you.